Good day everyone, I'm Jefferson Jairus from Group 22. Today I'll present about our assignment for Chapter 2, Question 2.1 regarding optical sensor calibration using cubic nonlinearity. The given calibration equation is fx equals x cubed plus 30x minus 31. The objective is to determine the correct operation point when fx equals 0 using two numerical methods, which is fixed point iteration method and Newton-Raphson method. The initial guess given is x naught equals 0 and all calculation must use 4 decimal places with approximate error less than 0.05%. First, for the fixed point iteration method, we rearrange the equation into x equal 31 minus 3 cube over 30. Using iterative calculation, the values gradually converge to the root. After 4 iterations, we obtain the final value of x4 equals 1.0000 with an approximate error of about 0.03%, which satisfies the stopping criterion. Next, we apply the Newton-Raphson method using the formula shown in here. The derivative of this function is f prime x equals 3x square plus 30. This method converged faster. After only 3 iterations, the solution also reached x equals 1.0000 with a very small approximate error. We also developed MATLAB code for both methods. The MATLAB output matched the manual calculation, confirming that our solutions are correct and accurate. From our comparison, Newton-Raphson requires fewer iterations and converge faster. However, fixed point iteration is simpler and requires lower computational costs. Therefore, for microcontroller-based sensor systems, the fixed point iteration method may be suitable because it uses simpler operation and small program size, which are beneficial for low power embedded system. That's all from me. Thank you.
Hi, my name is Numerical. So I'm from group 22. So for chapter 3, we got a medical device calibration curve in question 3.4. The action is, in biomedical engineering application, accurate measurement systems are very important because medical devices are rely on precise sensor reading to monitor condition. In this assignment, the wearable electrocardiogram ECG monitor use an analog to digital converter ADC to convert analog voltage signal into digital count. The calibration data of ADC were collected at interval of 0.5 voltage. The data given is the recorded calibration data are shown in table 1. The target value is voltage equal to 1.25 voltage. The selected interpolation point are first 102, second 205, and third 309 and fourth 4415. So the Newton divide difference interpolation formula used in this calculation. First order divided difference for B1, the answer is 206. B1 power of 2, the answer is 208, and B1 power of 3, the answer is 212. Second order divided difference for B2 power of 1 is equal to, and B2 power of 2 equal to 4. Okay. Third order divided difference, B3 power of 1, answer is 1.3333. Substituting the coefficient B0 equal to 102, B1 equal to 206, and B2 equal to 2, B3 equal to 1333. The interpolation equation becomes like this slide. The substituting x equal to 1.25, answer is 256.8125. Therefore, the estimated digital count using the Newton divided difference method is C equal to 256.8125. So, the substituting x equal to 1.25 for L0 is 0.0625 and L1 0.5625 and L2 0.5625 and L3 equal to negative 0.0625. MATLAB implementation program was used to verify the manual calculation for both interpolation methods. The MATLAB code store this voltage and digital count data, select interpolation point from 0.5 voltage to 2.0 voltage. Compute the Newton divided difference table. Evaluate the interpolation point. Compute the Newton divided difference table. Evaluate the interpolation polynomial at V equal to 1.258 voltage. Perform the range interpolation. Display the estimate digital count in the result table. So here is the result. The MATLAB successfully produced the same estimate value for both methods. The output obtained from the MATLAB was method Newton divided difference, estimate digital count 256.81, range interpolation 256.81. So the comparison of result, the three method, the answer is same, is 256.8125 at voltage 1.25. In conclusion, the jitter count at voltage 1.25 was successfully estimated using both the third order Newton divided difference method and the third order range interpolation method. Both manual calculation and MATLAB programming produce the same result. This confirms the accuracy and consistency of interpolation method used in this assignment. The comparison also demonstrates that MATLAB is effective tool for validation numerical method calculation. So that's all for me. Thank you.
Nama saya Ain Khadijah binti Arnizam, nombor metrik S73071. Hari ini saya akan menerangkan berkenaan dengan chapter 5 iaitu RC Charging Circuit. Untuk soalan A, kapasitor voltage adalah pada T sama dengan 0.6 saat. Mula-mula kita kena tukarkan persamaan ni kepada persamaan yang standard iaitu dV bahagi dt sama dengan 300 tolak 2V. Dalam international condition, T naught sama dengan 0, V naught sama dengan 0, N sama dengan 0.2, target masa T1 akan jadi 0.2, T2 akan jadi 0.4 dan T3 akan jadi 0.6. Untuk A1, Euler method, step pertama T naught sama dengan 0, T1 sama dengan 0.2. Jadi masukkan je dalam persamaan yang standard tadi. Jadi V1 akan jadi 0 tambah 0.2 bahagi 300 sama dengan 60.00. Untuk soalan 2, Hume method, kita ada dua formulation iaitu predictor dan corrector. Masukkan semula persamaan standard dalam predictor dan corrector. Jadi jawapan akhir untuk T0 akan jadi 48.00, T1 akan jadi 80.640, T2 akan jadi 83.2320 dan T3 akan jadi 102.5352 volt. Untuk soalan B, exact solution, VT sama dengan 150 darab 1 tolak E punca kuasa negatif 2T. T diberi ialah 0.6, jadi masukkan je, jawapan akhir akan jadi 104.8209 volt. Formulation untuk cari exact solution ialah true value tolak approximate value bahagi true value darab 100. Untuk Euler method, masukkan je nombor, jadi akhir sekali akan jadi 12.1914% dan Hume method, jawapan akhir akan jadi 1.3944%. Untuk C, Hume method is significant more accurate than the Euler method, yielding much lower true percent resolve error compared to Hume method.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hairul Iqwan bin Ahmad Shahid. My method number is S70351. So for today, I will continue for the chapter presentation for the question 6.2. So as shown in the question before, the current electric quantity in power electronic circuit is represented by the integration 0 to 2 square root 4 plus x power 2 times with the dx. So for the use for this methods in all calculation, we need to solve this question by trapezoidal rule with integration 1, 2, and 4. Using the answer from part A, we need to apply the rhombic integration. Then after that, we need to compute the percentage to error for the both methods by the new true value is 4.5912. Then after that, we need to determine which method is more accurate and to justify our answer. So continue to the manual calculation for trapezoidal rule implementation, as you see in my image behind me. So now that we understand our objective, let's go to step by steps. So the primary concept behind this method is to approximate the area under our function curve with the fx equal to square root 4 times 4 plus x power 2 by drawing straight line between point to create the trapezoid. So then this assumption is our formula that I use for this method. So then for problem, the boundary are fixed. Our limit a equals to 0 and our upper limit b equals to 2. Let's look at how our result change and improve with as we systematically increase the number of segments 1, 2, and 4. So we start with our simple estimation. Case 1, where n equal to 1, we only one segment. Our step size h is simply the entire width of the interval, which is 2.0. We just need to evaluate the function at the two endpoints. At x base 0 equal to 0, our function value f0 equal to square root 4 times 0, 2, which gives us 2.000. And our endpoint s1 equal to is ff2 equal to square root 4 times 2 power 2, which simplify to square root 8 or 2.8284. We are rounded to 4 decimal places. So after that, we plug in this boundary value into our formula, give us a t base 1 equal to 2 minus equal to 4.8284. Next, let's find our accuracy by splitting the area into two equal intervals. Case 2, where n equal to 2, And our which means our new step h drop to 1.0. This is a new intermediate evaluation point right in the middle at x equal to 1. So we calculate the intermediate value for f1 is equal to 2.23361, and our boundary value remain the same. For f0 is 2.000 and f2 equal to 2.8284. So according to the composite formula, any central point must be multiplied by a factor of 2 because it serves as shear wall between two adjacent trapezoids. Setting up our equation is t2 equal to 4.6503. 4.6503. So finally, push the trapezoidal rules to its limit for this assignment by calculating the case 3 where n equal to 4. So our h now is 0.5 when to keep the when the 5 coordinate point to evaluate. So for the first f0 is 2.00 is at the boundary, s1 is 2.0616 the interior, s2 is 2.32361 for interior, x3 is 2.5000 interior, then s4 is 2.8284 the boundary. Then our final composite equation with our rotor boundary and add them the two times the sum of all our interior points. So then the T4 we get a 4.6059. Then we need to notice that as our interval get higher and our trapezoid get smaller, the approximation steadily decrease and converge closer to the true values. For the next, we do the Roman integration and error analysis as you see in the manual calculation. Now that we have completed our trapezoidal estimate, we can move on to the part B. Instead of spending extra computational energy evaluating more coordinate along the curve, Roman integration takes our existing result, that is 4.8284 and 4.6503 and 4.6060. And then we use the Richardson expression to systematically cancel out the dominant error terms, the general formula written at the top of our sheet guides to this process. So as you see, our given formula for the TK, then we need to break down how this works. So we start at the level k equal to, which represent our first Richardson extrapolation column. We combine our first two trapezoidal exponential where n equal to 1 and n equal to 2. So our t, we gain a value of 4.5909. Then after we use the exact sum value, use our next pair of trapezoidal value where n equal to 2 and n equal to 4, then we gain the new t value is 4.5912. So then now we advance to level k equal to 3, which is our second Roman column. Then we take our new calculated Richardson value 4.5912 and 4.5909 and extrapolate them to eliminate even highest order error because k equal 3, our denominator factor increased to 4 power 3 minus 1 minus 1, which is 15. Then again our new t value is for 4.5912. Next step. So this brings us to the part C and D, error analysis and method selection. To see just how powerful this mathematical acceleration is, let's calculate the presentation through relative error for both methods against our benchmark. True value is 4.5912. So the first trapezoidal rule method with n equal to 4, our estimate was 4.06060. The error is calculated, and then we get the answer is negative 0.32%. This gives us a minor overestimation error of just 0.32%. For Roman integration, because our accelerated value perfectly converge to the true benchmark value of 4.5912, our true error drops to an absolutely 0%. So in conclusion, Roman integration is definitely the more accurate method. By analyzing the mathematical trend of our initial trapezoid area, it's completely wiped away the remaining 0.32% error, proving that a little bit of smart extrapolation goes a long way in engineering design. So then let's look at the trapezoidal rules. First, we increase the number of segments monotonically from n equal to 1 to n equal to 4. Our approximation steadily march toward our target benchmark. The true relative error dropped drastically for initial 5.70% at a single segment, all the way down to a minus 0.32% when using 4 segments. What's mathematically beautiful there is that every time we have our step size h, the remaining error was cut down by roughly a factor of 4. In numerical analysis, this exact behavior perfectly confirms our mathematical theory is proof that the composite trapezoidal rules operate with an expected 0 times h power 2. Convergence perfect, it means our manual integration and our code are behaving exactly as the law of calculus dictates. However, the true standout here is Roman integration by taking those baseline trapezoidal rule values and running them through the successive level of Richardson extrapolation. It produces a final result of 4.5911, leaving us with a true value error of a flawless 0.00%. Then ultimately our custom MATLAB script successfully crossed the validate our handwriting calculus, ensuring total algorithm correctness. Based on this fine tuning, we can completely confidently deliver our engineering recommendation. For the robot integration, is highly recommended for any complex engineering problem involving smooth mathematical function where high precision is vital. But the standard trapezoidal rule remains as excellent and dependable tool when you just need quick, low precision baseline estimates without any mathematical overhead. Okay, that's all for me. Thank you very much.